In this video, we'll take a look at an introduction to PCG compute shaders in Unreal Engine 5.5. We'll go over how to use HLSL with PCG to generate points that vary in size based on crevices and peaks of the landscape. To begin, we'll start with a brand new project and we'll go to Edit, Plugins, and make sure we have our procedural content generation framework loaded and enabled. Next, I'll quickly just create a landscape. I'll go here to landscape mode, and then I'll just load in a height map and offset my terrain to the right location and just import my height map, which now will produce a landscape that I can start working with. I'll also get rid of this floor piece since we'll no longer need it. I will also take our directional light and just angle it a little bit more to see the landscape shape a little bit more clear. And next I'll create a PCG volume, which will be the area that our PCG will evaluate. I'll try to size this and fit this to wrap around my terrain. Now I'll right click in my content browser and I'll go to PCG and create a PCG graph. And I'll call this something like PCG underscore gradient scatter. And we're going to open up our PCG graph. And once we've opened up our PCG graph, we're going to want to get the information from our landscape. So to do that, I'm going to right click and create a get landscape data node. The next thing I'll do is create another node, and I'm going to create a custom node. So I'll search custom, and under custom HLSL, we'll create a custom node. Now there's different behaviors of this node. It could be a different kernel type. It could be a point processor or a point generator. In this case, we want to generate a fixed number of points along our terrain. So we'll change it to a point generator and specify some points. And maybe for now, we'll do 8,192 points. We can change that later, but this might be something we can start with to scatter that many points over our terrain or our landscape. But at the moment right now, this isn't really doing anything. We're just defining the number of points that it will generate, but we also need to define our input and output pins. In this case, we're going to keep it very simple. Our input we know is going to be our landscape data. So we'll go to our input pins. We'll open it up. That's our pin here called in. You can see the label is called in. We're going to change the allowed type from point to landscape. And you'll see that changes some code down here that we'll talk about. There's these helper functions and a bit of a list of things that we can use that they give us. There's like helper declarations, there's output declarations for if you need an output point position or rotation or scale. So it gives you some functions that you can use. And then same with input declarations. It gives you functions that you can use. How can you get the height of points from your landscape data? Well, it has functions here called get height, get normal, and it gives you an idea of what variables exist and what functions exist that you can use within your HLSL. So we're going to make sure we do that. We're going to make sure we set our input to be type of landscape, and then we can connect it up. And then our output we're going to leave as points, because we're outputting points, and then we can attach a model to those points or a mesh or something to those points. Now that we have that, we can start writing our code. Now you can also add your own shader functions here or your own functions, and then there's the actual source of your shader or your code. But we're not going to add any functions right now. We're going to keep this really simple. It's more of an introduction to how to start using this stuff to build up something that actually outputs a proper result. So the next thing we're going to do is open up our source editor, because it's probably a lot easier to type in the source editor than in this text field here. So the source editor will allow us to see the declarations with syntax highlighting. It will also allow us to type here and put our shader code and get some syntax highlighting. So this is probably where we want to type our code more easily. I'm still going to use Visual Studio Code just because I like having the line numbers, and it'll probably be easier for you to read when watching this video. So I'm going to jump over to Visual Studio Code and start typing up our code. Now, before we start typing our code, we have to have a clear idea of what we want to do or what we want to start off with. So first thing that I know is that we have our PCG volume, and we have to get maybe the length and width of it, or its bounds. And then within its bounds along our terrain, we have to generate some points. So I'm going to look at my helper functions here, or helper declarations, and you'll see that there's a section here called get component bounds min and get component bounds max. That will get us our world space bounds of our PCG volume. So I'm going to use that, and then I'm also going to use the create grid 2D function here to create a grid of points along our terrain, and then using the component bounds min as the minimum and component bounds max as the maximum. And the number of points is already defined, which we can see up here. We defined it here, and it's here as a variable. So we can just use that variable num points. So we can start using these to start generating some points and building up something to start with. So I'll go over to Visual Studio Code, and we'll start off with typing our code. So I'll create a float for the bounds min and a float for the bounds max. I'm not making it a float 3 because I only really care about width and length. I'm not really, I'm generating a 2D grid of points, so this will probably work fine. And I can do get component bounds min and get component bounds max. And there we go. We have our bounds as variables. And then next I'll create a float 3. So that's our position of our points that we're going to create, and I'll call it point location. And we'll create a 2D grid. So create grid 2D. And if I look back at that helper function here, create grid 2D, you can see it takes element index, the number of points, and then min and max of the bounds. So create grid 2D, element index, I can just leave that as is. Then I do number of points that we want to create. And then we do our bounds min and bounds max that we defined up here. And that's really it. And that should create our points. But technically, this won't give us really any output yet because we have to output those points. But we're starting to create that. We're starting to get this working. So the next thing that we're going to do is maybe output those points and just see if this works at all. So as an example, I'm just going to go back to Unreal, and we'll take a look at the output declaration. So you can output the set position here. So out underscore set position. Out is our name of our output here, as is out underscore. And if you do change the input labels or the output labels, these functions or declarations here will change. So you have to be aware of that. In my case, it's out and in because I left it as default. So I can do out set position, and then you set the data index, the element index, and the position. So if I were to go back into Visual Studio Code, so now I can output those points. I'll just do out underscore set position, and I'll do out underscore data index, element index, and then point location. That location of all the grid of 2D points that we created. And that's really it. And if we take that, copy it, go into Unreal, into our PCG graph, go into our custom HLSL node, we can paste that into our shader source. Shouldn't get any errors. We can save that. And then I'll go to our PCG volume and connect it up. So under the PCG component here, we'll go to the graph, and I'll drag and drop my PCG gradient scatter graph into there. And now we'll have to go back to our graph and take our custom HLSL and right click and debug it so we can see some temporary output of those points. And if we do that, you don't really see anything yet, probably because those points are so small. So I'm going to scroll down to the debug section, and I'll change the debug scale method from extents to absolute, and maybe I'll use a value like 5. And it's a bit hard, we can't see, probably because these points are just being created at 0 height as well. They're probably there, but I probably can't really see them. And just to make sure, we'll save this graph. We'll go to our PCG volume. We'll click cleanup and generate just to refresh everything. Oh, and there we go. I can see those points and they're just really low in world space. So it's creating our graph. If we just want to temporarily offset those points, I could just go in here and take my point location.z and just add like 100,000 units to it. And now it would push it up. And we can see all those points that it created. So we know that it's working now. So I'm going to leave that there, but at least we know how to output points. We know that it's working with our bounds. So how do we actually make this code more proper? Like how can we actually make it do something more functional like we wanted to, where it can kind of check the height and see what areas are lower or higher. And for those areas, spot a model or a point with a different scale. So now we know the basics. We know how to generate some points and output them. But how do we start using this and adding other stuff to make the output something that is more useful? So next thing we're going to do is just remove this out set position. We don't need that right now. And what we want to do is get the landscape height at each point's location. So again, there is a function for this. If we go back to our PCG graph on our custom HLSL shader, under input declarations, you could see here there's a function called in get height, and it'll get the height for the landscape at that position. So we're going to take that and utilize that. So we're going to go here and make a variable called height, and we'll make it get the landscape's height at our created point location. So something like that. And then what we're going to do is create a filter size, and this filter size will be how far from that point in X and Y do we search for neighboring points or other points around that area. So we're going to do a static constant float 2 because this value won't change. It'll be called filter size, and we'll make it equal float 2 values, one for X, one for Y, and it'll be 1 and 1. So the filter size of 1 and 1. And you can change that filter size and get a different look of this patterning that we're going to be doing. But we'll start off with that as a starting point. So now we're going to use that filter size and offset the surrounding points in left, right, up, and down. So we're going to do a float 3, and it'll be called offsets. And there'll be 4 kind of sets here of that. One for the left direction, so that will be something like float 3, negative filter size X, and X refers to the first entry, this one. Y will refer to the second entry, that one. So we'll do that, and then 0 and 0. And then we do that for pretty much all the other directions. So I have left, I'll do right, I'll do down, I'll do up. So left, right, down, up, and then we just swap this around. So negative, positive, and then negative y, and then positive y. So something like that. And then after that, what we'll do is we'll sample the height at each one of these offset points. So we'll do float heights, and same thing, 4 values, and we'll just use a for loop. You could type this out, but I'm pretty sure the compiler will choose whatever is best, but this will be less for me to type. So I'm just going to do a for loop and then use my heights and loop through it 4 times for the 4 different heights, and then get our height at our point location but with our offset applied, like that. Now we want to make sure our spelling is correct. I could see I used offsets here. Here I put offset, so I'll add a S. Let's make sure everything's typed correctly. Coding is always case sensitive, and missing a semicolon or anything can cause issues. Like at the end here, I probably shouldn't have a comma since that's the last one in this kind of row of values in this kind of array. So make sure you don't have any issues that are outstanding in your code. And then what we're going to do is we're going to take all those offset heights and we're going to produce the average height for that area as a value. So we're going to do float average height, and I'll make that equal our heights 0 plus heights 1 plus heights 2 plus heights 3. And after doing that, we'll probably want to make sure this is actually averaged. So there's 4 things here, 1, 2, 3, 4. And what we want to do is just divide that by 4, but usually division is slower than multiplication. Again, the compiler might automatically adjust things to be more performant, but just to be safe, I could just manually multiply it by 0.25. So it does the same thing as dividing it by 4 or 4 things. So that gives us our average height for that area. It's offsetting in these different distances from that original point in left, right, up, and down. And it's taking the heights of all those points and getting the average height in that area. So that's what this is here, our average height. And now that we have our average height, we want to get the difference from that average height. So the way that we're going to do is we're going to make another variable called float diff height. And this will be our difference from the average height in each of those directions. To the left of the point, to the right of it, above it, below it. So we're going to make this variable. We'll do another for loop just so it's less typing. We'll do it int I equals 0. We'll just do a quick loop. I is less than 4, I plus plus, and diff height, and we'll make it equal saturate. So saturate will clamp between 0 and 1, make sure we don't get values above 1 or below 0, and we'll take our average height and we'll minus our heights. So what that's doing is it's taking our average height and then minusing the specific height at that location. Therefore, we only get the difference remaining. Now that we have that difference, we're going to create a mask variable. And this mask will contain the difference of the average height and their original height. So we're going to make it do the same thing, saturate, so it clamps between 0 and 1. And we're going to take our average height, we're going to minus the height of our specific point that we're on, not the one offset above or to the left or to the right or below, but the point right in the middle of those offsets, the original point. And we're going to take that mask and we're going to smooth it out by adding the surrounding points differences. So it's kind of acting almost as like a blur or like a combination of those points in that area. So we're going to do a float smooth mask because we're going to kind of smooth it by adding the surrounding points. And I'll make that equal our original mask here, which is the difference between the average height and its current height. But then we're going to also add the surrounding offset differences as well. So we're going to add our diff height 0, and then 1, and then 2, and then 3. So 0, 1, 2, 3. Now, since we have a bunch of things here, the smooth mask, we don't want this ending up a super bright value. So we have 1, 2, 3, 4, 5 things all added here. So maybe we'll average those out as well. So I'll multiply that by 0.2. And now we have our smooth mask. It's pretty much our differences of our point's heights from that original point and some surrounding area of it all added together to produce a value. So now what we're going to do is use that smooth mask to determine how big these points that get outputted are. If the difference in height is larger, it's going to create a larger object or a larger point size. So to do that, we're going to do a float scale variable, and we're going to make it equal our smooth mask. And we're going to check if our smooth mask is bigger than a certain value. If it ends up being smaller than that value, we'll just output a point with 0 scale, which pretty much means like no point, we won't see anything. Otherwise, what we're going to do is lerp or blend between two values, our minimum and maximum value for scale. So maybe the minimum will be 0.5, the maximum will be something like 50. And what we're going to use to determine what in that range we end up choosing, we'll use our smooth mask, and we'll saturate again just to make sure it gets clamped within a range of 0 to 1. So something like this. And then, if it doesn't fall within that range, if it's smaller than that value, then we just end up outputting 0. And now we have our scale value set up. Now, finally, all we have to do is also make sure our point location is at the correct height. So we'll make our point location Z value equal the height of our landscape. And then we'll also output our points. And that's our final step. We'll do out. We'll set our position. Our position will be our, first of all, out data index, then element index, and then point location. And then we have to set our scale. And again, you can check these if we go back to Unreal and we take a look at our declarations here, output declarations. Where's that set position? There it is. Where's our set scale? Here it is. Set scale, data index, element index, and then scale. So same thing in our code. Out, set scale, and what we do is our out data index, element index, and then our scale. And that's really it. And now if we take all our code, we go to Unreal, we paste it in here for our shader source, check if there's any errors, click force regen, save, no errors, and take a look at what we get. Okay, there's our debug view of our points, so they're going to the correct height. Now we don't really see the scale because the scale won't show in our debug view. So what I'm going to have to do next is after our custom HLSL, I'll undo the debug view. And what we're going to end up doing is adding our static mesh spawner. So we can actually attach a mesh to these points. So I'll do a static mesh spawner. I'll connect that up to our custom HLSL. And I'm going to do a mesh entry. What am I going to use as my mesh? For now, I'm just going to search and just use a sphere. So maybe, what do we got here? Editor sphere. That should work fine. And I'll click save. And we'll take a look. And there we go. All our points ranging in different size based on the difference in that averaged area. And that's looking pretty cool. So if we go down here, we can see all those points, and that's pretty neat. So you can use this to start to kind of process points on your terrain and create different sized objects or plants or things on the edges of peaks or on the crevices of areas. And this is just an example of what you can do with these PCG compute shaders, but there's plenty of other things they could be used for. Now, one thing just to jump back to, if we were to take a look at this and up our point amount. So I'll go to my custom HLSL here and say number of points, let's go crazy. Let's do 128,000 points. And let's save that. And my performance is going to plummet. So it looks like it's working, but the performance is really bad right now. Now to speed that up, we could introduce culling. We can go to our static mesh spawner and we can go in here to mesh entries and add some culling. So points that are super far away get removed. So I can go to instant start call and instance end call and change that to something like, maybe 30,000 and then 40,000. Oops, one extra zero. There we go. And save that. And then it'll call points that are too far away, and my performance is good again. And then it just spawns the points as you walk along the terrain and get to areas that are closer to you. So that can really help out performance. And if you go really far away, you won't see any of those points. But again, if this was scattering like grass or rocks or something, it might not matter because there's probably a bunch of other objects blocking it, and you're probably running around the terrain. If you enjoyed this video or you learned something new, don't forget to like and subscribe and comment down below. And if you are part of the Patreon, which you can find a link to in the description below, you'll also get access to the PDF for this video that goes over all the steps in a little bit more detail.